Welcome to the NHERI SimCenter's Live Expert Tips. In this session, we introduce you to exploring, calibrating, and propagating uncertainties through finite element models using quoFEM. Our expert today is Dr. Aakash, Bangalore Satish. He is a postdoctoral researcher at UC Berkeley with the NHERI SimCenter and a lead developer of the quoFEM application. Aakash received his PhD from the Department of Civil and Systems Engineering at Johns Hopkins University. His research interests include Bayesian estimation and model selection and averaging. Aakash, thank you for being here.
Thank you so much, Matt. Hello and welcome all to today's session of the Live Expert Tips series. So today's talk will be about using quoFEM to explore your finite element models and then to calibrate the finite element models, as well as once you've calibrated and even before calibration, how to use quoFEM to do forward propagation of the uncertainties that are in the inputs to your computational models. So in today's session, we don't expect you to be familiar with any of the SimCenter tools before. So I'll briefly give an overview and a brief introduction of quoFEM and how to use our tool as well. So if you are not familiar with this, so the SimCenter is part of the network of research infrastructure funded by NSF under the NHERI program, which stands for the Natural Hazards Engineering Research Infrastructure Program. Under this program, the mandate of the SimCenter is to advance the capabilities to simulate the impact of natural hazard events on structures, lifelines, and communities. In order to achieve this objective, the SimCenter has developed an open source framework for building software applications that support computational modeling and simulation in natural hazards engineering. And the center releases desktop applications that have been built utilizing this framework. And these applications support various needs, from acting as a UQ enabling tool for user-defined computational models, which is the quoFEM tool that we'll be discussing today, to apps that support developing models of structures, as well as assessing the response to input loads caused by various natural hazards, such as the EEUQ tool or the VEUQ tool or the HydroEQ tool. So these are used to assess the response of structures to the impact of several natural hazard events. Also, there are apps that, in addition to those capabilities, the PBE app enables estimating the performance of these assets under the natural hazard load. And the R2D tool supports regional scale analysis of infrastructure under the action of natural hazards. So these are some of the desktop applications that have been developed and released from the by the SimCenter. In today's talk, we will focus on quoFEM. So quoFEM the acronym stands for Quantified Uncertainty and Optimization for the Finite Element Method. This is a desktop application which has a user interface, a graphical user interface. And the starting point to use this tool is to have a user-specified computational model of the problem that you're interested in. So that can perform one deterministic simulation. So it accepts one value of the input parameters of your model and generates the output quantity of interest that you are interested in. So this is the requirement. So you have a user, you are supposed to develop a computational model. And once you have such a computational model, say in this model, I'm interested in determining the interstory drift response time history of a structure subjected to some ground motions. So then your computational model will be a script that builds the model, applies the ground motion, simulates the response to that excitation. So that is your starting point. Once you have such a computational model, if you then want to perform probabilistic analysis using that model, for example, if the input parameters of the material model used in the structure are uncertain, then what would be the resulting uncertainty in the peak interstory drift? So this is where quoFEM can help you. So once you have such a model, quoFEM can let you plug in your computational model into several UQ algorithms that will help you conduct several UQ analyses. So for example, so these are the different types of algorithm UQ methods that come under the umbrella of the forward problem. So in UQ, in quoFEM, so once you know once you specify the uncertainty in your inputs to the model through probability distributions, quoFEM will let you propagate those uncertainties in your inputs through the model to the final response quantity of interest. So this is done by drawing random samples of the input values, and for each sample running one deterministic simulation corresponding to that uses that sample value as the input to the model. So that is known as uncertainty propagation. And at the end of the process, quoFEM gives you several statistics that summarize your output quantity of interest, such as what is the mean value of the response, what is the standard deviation of the response, and so on. So that's the kind of outputs that you can expect using when you run the forward uncertainty propagation. Now, another type of forward analysis is known as sensitivity analysis. So if there are several input random variables, the randomness in the inputs results in randomness in the outputs. Now you would want to if you're interested to then find out what is the contribution of each of those input parameters to the randomness in your outputs, then you would run what is known as a sensitivity, a global sensitivity analysis. So this is another kind of analysis that lets you understand the influence of the different input parameters in your model on the response quantities of interest. So in today's demonstration, in today's example, so we will be showing how to do forward uncertainty propagation as well as how to run a global sensitivity analysis in quoFEM. So these will let you explore and understand your model. And quoFEM always treats the models as a black box. So the algorithms that we develop can be used with with the computational models that are developed in any of the languages or any of the modeling engines that we support. Another kind of forward problem is what is known as reliability analysis, where you're interested in computing what is the probability that your response quantity of interest exceeds a certain threshold. So these are the types of forward problems that you can use perform using quoFEM once you have a computational model. Now, in addition to that, if in addition to a model, you have some data and you are then interested in calibrating the values of the input parameters of your model so that the output that is produced by the model matches the data that you have observed, that you're using in the calibration process. So this kind of a problem is known as an inverse problem. And quoFEM supports two types of methods for solving inverse problems. So one is just a deterministic method of calibrating the parameters of your model to best match the output data that you have observed, the calibration data that you observed. In the other method it's a probabilistic calibration method, which is known as Bayesian calibration. So in this method, you specify some inputs, uncertainty in the inputs prior to observing the data, and you want to now update your uncertainty about the best parameter values once you have observed this data, once you have seen this data. So this is also supported in quoFEM, and in today's example, I'll show how to run Bayesian analysis using quoFEM. Now, all of these kinds of EQ analyses they would require evaluating your computational model several times, like very large number of times. So in order to support this, quoFEM lets you run analyses using the high performance computing facilities that are provided through TAC. That's also part of the NHERI network. So if you have a design safe account, quoFEM will let you, and once you have these models, quoFEM will let you do UQ analysis on the cloud, which is kind of a requirement if you want to do lots of UQ analysis. Now, in addition to that, sometimes the computational models might be so expensive that even with high performance computing facilities, you might not be able to achieve the number of UQ simulations that you want to do. So to facilitate with in such cases, like quoFEM also supports surrogate modeling. So this is where you develop an approximation of your computational model. So you develop a relationship between the inputs and the outputs, and quoFEM lets you train these surrogate models, which are then much faster and easier to evaluate than running your computational model. So quoFEM supports surrogate modeling. And once you have a surrogate model, you can then use that surrogate model within quoFEM to perform forward analyses. And we're working on using surrogate models to perform inverse problem Bayesian calibration. So that was just an overview of the different UQ methods that are enabled by quoFEM. Now, as I was saying on that previous slide, so quoFEM supports several UQ analyses. And quoFEM also supports several computational models. So the user can define computational models, which are scripts that are written in different modeling engines, such as OpenCs or Python. So for example, you might have your computational model can be just a Python script, or within that Python, you can also have an OpenC Spy model or something like that. So these are the different kinds of computational models, and quoFEM lets you plug in those computational models into the different UQ algorithms that I showed on the previous slide. So these were the three forward propagation methods that were supported, and these are the two inverse methods. And these are the surrogate. This is the surrogate modeling option. In addition to that, I won't discuss this custom UQ method today. But this is also a more detailed list of the UQ algorithms that are supported for each of these UQ methods. So to do forward sampling, you can use either Monte Carlo simulation, which is just drawing samples at random from your input parameter space, or you can use Latin hypercube sampling, which again is a space filling design that lets you sample your input parameter space and run simulations of your computational model. So in order to do the uncertainty propagation a little bit more efficiently, quoFEM also lets you use Gaussian process regression or polynomial chaos expansion. So these are surrogate models that are trained using samples of the input and output response from your computational model. And then you can use these surrogate models to do the forward uncertainty propagation. So these are the different methods available to do forward sampling. And under global sensitivity analysis, you can either use the probability model-based DSA, or if your dimensions of the problem are very high, so you can reduce the dimensionality of your output by doing principal component analysis. This is implemented in quoFEM. So there are methods that will let you handle, that will let you perform global sensitivity analysis when the dimensionality of your output is high. And this is another method that is available through Dakota that lets you do global sensitivity analysis. In addition to that, there are several algorithms that support reliability analysis. I'll not go into the details today. Now, when you're coming to deterministic calibration, there are two algorithms that are supported in quoFEM, which enable you to do gradient-based least squares minimization. So in these calibration methods, they work on minimizing the least squares, sum of the squared residuals between your model predictions and the observed calibration data. So these are gradient-based methods. But sometimes you might not be able to calculate the gradients in your model, or your the response might not be continuous, so gradients might not be defined. So quoFEM also supports gradient-free optimization methods that can be used to perform parameter model calibration as well. In addition to having, in addition to supporting gradient-free methods, these will also let you define your own objective function. So it need not just be the sum of the squared errors that you want to minimize. So you can define some other like likelihood-based objective of your interest. So you can define any objective that you want and use this optimization algorithm, the gradient-free optimization algorithm, also with quoFEM. So this is another feature that is available. Now, when it comes to Bayesian calibration, the uncertainty which is in the updated uncertainties, is called the posterior probability distribution, and that is typically characterized by drawing samples from the posterior probability distribution. So these are two methods that are supported in quoFEM that let you draw samples from the target, which is the posterior probability distribution. In today's demonstration, I'll show how to set up analysis using the TMCFC, the transitional Markov chain Monte Carlo method, to draw samples from the posterior. And these are the different options that are available to develop a surrogate model within quoFEM and then use that for forward propagation within our tools. So this was just a brief, this was an overview of what are all the methods that are supported in quoFEM. Now we have, if you are interested to learn more about these methods, there are lot of recorded sessions such as the previous live expert tips. So there have been sessions on how to do global sensitivity analysis on a structural system, as well as how to do global sensitivity analysis for high dimensional outputs. So those are the two different problems that I highlighted on the previous slide. There is also an educational module that is available. So all the links will be on these slides, and the slides will be shared with you so you can refer to. And these are available on our tool web page. So if you search for quoFEM, you will find the links to all of these previously recorded live expert tip sessions. And for more details on how to calibrate material models in OpenCSU, that is also one of the previous live expert tip sessions that is available to you. So with this, before I get into the example, let me demonstrate how you can get quoFEM. And so if you do a search for quoFEM, it will take you to our to the homepage of our tool. So you will find links here that will let you download the application. So if you have not yet downloaded quoFEM, so this is where you will find quoFEM. So I just downloaded quoFEM yesterday, and the last released version of quoFEM is version 3.2, which was released on October 11, 2022. So this is how you'll find quoFEM. Now, on the home page, in addition to the links to download the tool, there is also a link which takes you to our documentation page for quoFEM. So here you will find details on how to install, and also there is a tutorial which will help you get started with quoFEM. And there are also user guides with details of all the different UQ methods and the FEM engines that are supported. And there is also a manual of examples that are available on our documentation webpage. So you can refer to all of these to get started. And in addition to that, this is where you will find the recordings of the previous live expert tip sessions, as well as the previous tool trainings that have been conducted for quoFEM. So this is on our NHERI SimCenter homepage, and you will also find links to all the other applications that we develop similarly. So if you're interested to explore some of our other tools, you can do that. Now, once I download quoFEM, I'm using a Mac, so I'll get a DMG file. And then if I open that DMG file, so this is the quoFEM application. So I've just copied it to this directory here. Okay, so after opening the tool, this is how the quoFEM tool looks like. So all of our desktop applications have a similar visual aesthetic. So this is how the tool will look like. There are 5 panels in quoFEM that you can navigate through. So the first panel, called the UQ panel, is where you select the different kinds of UQ analysis that you want to do. So as I pointed out, these are the different methods that are supported in quoFEM. And we have these methods available through Dakota. But there are also additional options that are available through other so-called UQ engines. So for example, if you select the SimCenter UQ engine, you can then do also training of a surrogate model of a Gaussian process surrogate model, or training another kind of surrogate model called the PLOM model, which stands for probabilistic learning on manifolds. And if you select the UCST UQ engine, so this is where the TMCMC or the transitional Markov chain Monte Carlo method is available to you. So once you selected current the UQ method that you want to use, you will then enter the arguments to set up the UQ algorithm within the UQ panel. And the next panel is called the FEM panel. So this shows the list of the different finite element modeling engines that are supported. And here you choose what is the input script that runs one analysis of your model. In addition to the input script, you can optionally provide a post-process script, which you can then use to process the outputs from that model to write the outputs to a file that is needed by quoFEM. So in order to interface your model with quoFEM, you have to write the outputs from your model to a file called results.out that you can do using a post-process script. But this is optional. You can do all of these tasks within your input script itself. Now coming to the RV panel, so this is where you define what are the input probability distributions to the parameters or the random variables that are part of your model. So if you, let's say I just randomly define a variable with some distribution, you can also then visualize the probability distribution that you just specified. And this panel, known as the EDP panel, is where you define the quantities of interest. So you can give names to the different variables that are the output quantities from your model. And they can be either like just scalar quantities, or they can also be vector quantities. So you can have time histories as your output quantities of interest. And once you run an analysis, the results will show up in the results panel. So once you have downloaded quoFEM, this is how you can do a quick check to see if everything has been set up correctly. So there is a panel here which contains a lot of examples that are already shipped with our tool. So if you click on the examples panel, you will find a list of several examples that ship with the tool. So all the files that are needed to run this analysis are already available that come along with the tool. So for example, if I click on this, the first name in that list, that will load an example that will let me do forward propagation using a two-dimensional truss. So the details of this example are also on our documentation. But once you click on that file, it is going to automatically populate all the, it's going to set up the analysis for you. So for example, if you want to see where the finite element model, where the example file is located for this problem, you will see the full path to that finite element script in the FE panel here. You can go ahead and inspect how the model looks like. And these are the four parameters that are input random variables in this problem. These are the two output quantities of interest. So this is how you would set up a forward propagation problem. And when I click on the run button, quoFEM then will start running your problem in the background. So all the analyses are run. If you want to find out where the analysis are run, so you can go to the preferences panel in quoFEM. And within this preferences panel, you will find the location of your local jobs directory. So this is where all the analysis are run locally on your machine. So when I just ran this analysis, quoFEM created these files within our local work directory. And I had requested 50 samples. So it created 50 working directories, and within each working directory, quoFEM runs one deterministic simulation. So this is how you can access the files that are created during the process. But after running the forward propagation analysis, you saw that the results panel was automatically displayed. Now this results panel first contains a summary of the different summary statistics of the output quantities of interest. So there were two output quantities of interest that were defined. And you can also observe a table with all the 50 sample input values and the corresponding output values. So this is the kind of results that you can expect from quoFEM. Now I'll just go back to the the slides. So in today's example, we will show an example that is calibrating a soil material model that is capable of demonstrating liquefaction response. So in this example, we have some data that is coming from a cyclic simple shear test, and the data is shown. The data is available in the reference, is described in the reference shown here. Now, in the cyclic simple shear test, there are a number of, so the test is performed by several different cyclic stress ratios. So the cyclic stress ratio is the ratio of the shear stress that is applied to a soil sample to the vertical stress. And here I show a schematic of the experimental setup and how the soil specimen looks like within that experimental setup. So in this test, the amplitude of the shear stress is held constant, and cyclic the shear stress is applied in a cyclic manner. So this is experimental setup, and we want to develop a computational model that simulates this experimental setup. So to do that, we have an OpenC script file, which has a single element, which is trying to replicate whatever happens within this soil specimen during the test. So within this script in OpenC, we choose to model the material using the PM4 sand material model. And we use a single element, which is of this type, which is a 4-noded quadrilateral element. And in this material model, there are a total of 24 parameters. Of these 24 parameters, only 3 parameters are considered to be the primary parameters of this model. And from this data, this is the experimental data of the cyclic stress strain response. From this data, the only value that we're interested in is what is the number of cycles that have occurred until the onset of liquefaction. The onset of liquefaction is defined as whenever the shear strain reaches a value of a particular threshold. Here, that threshold value is 3%. So whenever the shear strain reaches a threshold of 3%, that is considered to be the onset of liquefaction, and the number of cycles till the onset of liquefaction is counted, and that is the data. So we can get this data from the experiments, as well as whenever we run a simulation, we can find out how many number of cycles are needed until a shear strain of 3% is reached. From these data sets, from these points, we can get this curve, which is the cyclic strength curve of the soil. So here, with the black dots, we have shown the calibration data that is used, which is coming from the experiments. And for any particular value of the input parameters, it produces the results from simulation, which also give the number of cycles to the onset of liquefaction at these CSR values. The objective of this problem is to now calibrate the values of the input parameters of this material model so that we minimize the residuals, so that we match the data that was obtained experimentally. Now, before we calibrate the parameters of this material model, we will do a global sensitivity analysis using quoFEM. So by doing global sensitivity analysis, we can screen out parameters of this material model that are not important to determine the cyclic shear strength. And once we identify which are the important parameters, and we can then calibrate only the values of those parameters using Bayesian estimation in quoFEM, using the cyclic strength data of the Ottawa sand. So that is part one of the problem. And then once we have calibrated the parameter values of the PM4 sand material model using that data, we would then want to use those calibrated parameter values and estimate the uncertainty in the residual lateral displacement of a layered soil column subjected to seismic excitation. So this is going to use a different computational model. So in this, for this, we will then propagate the uncertainty that is remaining in the parameter estimates after Bayesian calibration through a model of the layered soil column. This layered soil column rests on bedrock, which is sloping at an angle alpha, and it is subjected to some ground motion at the base. Under the action of these ground motions, at the end of the application of the ground motion time history, we are interested in finding out what is the residual displacement of the soil column along the profile of the soil column. So this is what the second computational model is doing. Now I'll again go back out of the presentation to the demo. All the files that are needed to run these analyses have been posted. I'll show where you can find those files. So so this is the SimCenter forum, which can be used to ask questions or to raise feature requests and so on. So under the SimCenter forum for quoFEM, there is a post which is for user-to-user file sharing. So under this post, I have shared the examples that are going to be used in today's demonstration. So I'm going to download download that zip file. And within that zip file, you'll find that there are 3 folders. So let me just move this to this directory. Okay, so within, so you will all be able to access all that file as well. So within that file, there are 3 folders. We will use the same model of a single element for the Bayesian calibration as well as for the global sensitivity analysis. Now, within the global sensitivity analysis, if you see what we are doing in one simulation, we are describing the model using an OpenSea script file that is written in Tickle. So here we first define the material model parameters of the PM4 sand model. And then we define what are the list of what is the list of the CSR values at which we will run the simulation. And then for each value of the CSR value in that list, we perform the cyclic direct simple shear test by sourcing this script. So the script runs one cyclic simple shear test. So that's also shared in the list of files. And after the simulations are done, we write the results to a file called results.out. So this is important to interface with quoFEM, to interface your model with quoFEM. So typically, the way you would set up, the way you would define parameters is by using the set keyword in OpenSea. But in order to interface with quoFEM, so in order to let quoFEM know that which of these input parameters is the subset of parameters that you want to calibrate, so you use the keyword known as pset. So instead of the keyword set, so you just change, you just define the input parameters of your model by using the keyword pset instead of set. So this is the only change that you need to do to your model script in order to let quoFEM know what are the input random variables in your problem. And you also have to ensure that you write the results of the analysis, so those are the EDPs that are the quantities of interest that are defined in the EDP panel. So you have to make sure that you write those results to a file known as results.out. So this is how you can interface your computational model with quoFEM. So those are the only 2 steps that you need to do. So it's pretty simple to be used, at least we hope so. And we have seen that even like undergraduate students are able to use quoFEM So all the examples that I'm showing were actually done as part of a REU program over a couple of summers ago by an undergraduate student. So we hope that you will see that quoFEM is easy to use, and it's meant to be used even by beginners to UQ applications. So you don't need to be a UQ expert to use our tools. Okay, so that is the script that will be used for global sensitivity analysis. Now, in addition to that, if I click on the Bayesian calibration folder, you will find the same two scripts that are being used to do the Bayesian calibration as well. In addition to specifying the model, in Bayesian calibration, you need to also define the calibration data, which is just a text file here. So this contains the 6 data values that were obtained from the experimental results. So these are the 6 number of cycles, the onset of liquefaction at the different CSR values that we'll be using during our simulation. So this is how you set up your calibration data. So it's just a single row with all the values that are part of your problem. So in order to set up your in order to make it easier to run the analysis on the problem, there are these JSON files that are also present in each of those directories. So in quoFEM, you can open and you can also save the results to JSON files. So I clicked on open. So I'm going to, if I navigated to the Bayesian calibration folder, which will let me open that JSON file in quoFEM. Now within this JSON file, I have defined all the inputs that are required to set up the GUI. So I defined what goes in the FEM panel, what goes in the UQ panel, what must be there in the EDP panel, and what are the random variables of the problem and so on. So whenever you set up something in quoFEM, if you click on File, Save or Save As, you can choose some name. And quoFEM will automatically save the inputs into a JSON file. So this is how this JSON file was created actually. So I set up the problem. I populated all the different fields of the different panels. And then I saved the GUI specifications into a JSON file. So that will let you create a JSON file. And you can, whenever you need to run the analysis again, the next time you don't have to again start from scratch and define all the inputs in these panels. You can just load the setup of the problem that you have saved into a JSON file. So I just opened that JSON file and it auto-populated all of these values. So this is the calibration data file that will be used for the problem. And we will be using the UCST engine to do TMCMs, transitional Markov chain Monte Carlo, for the Bayesian calibration with 500 samples drawn from the posterior. So you can also specify a seed. The seed helps to ensure reproducibility. So once you run an analysis, since you are doing probabilistic analysis, every time random values are drawn for your inputs. But if you want to ensure reproducibility across different runs, you can achieve that by setting a seed. So the next time when you set the same value for the seed, it will generate the same sequence of random variable sample values that will be passed as input. So you'll be able to reproduce your analysis. So these are the 3 required inputs to the problem. And in the FEM panel, this shows that we will be using the analysis script.tickle as the input script for this problem. And in the RV panel, it shows that there are 3 variables that will be used in this problem. And in the EDP panel, again, there are 6 output quantities of interest, each of length 1. So all of those are defined. Now, each of these model evaluations takes about a minute to run. And if I request 500 samples to be drawn from the posterior, it needs to do around like 30,000 model evaluations or more. So since we don't have that much time to run this on locally on our machine, we can run these jobs at design safe. So if you have a design safe account, you can, by clicking the login button here in quoFEM, you can log into your design safe account within quoFEM. And once you do that, you can then submit this job to run on design safe's HPC facilities. So if you click on run, the jobs will run locally on your machine. But if you click on run at design safe, then it will open up a window here where you will give your job some name. So I'm just going to call it Bayesian calibration. And you can choose how many nodes you want to use on the HPC facility supported at design safe, and how many processes you want to use per node. So let's say I've requested 500 samples here. So I'm going to use 5 nodes, and I know that on design safe, we run these jobs on Frontera. That's the name of the supercomputer that we use to run these jobs. On Frontera, per node, there are a maximum of 56 processors. So I will run 56 processes on the node. And you also need to define what is the maximum runtime for the job that you want to define on design safe. So if you exceed that runtime, the job will be killed. So make sure that, so to do this, you have to run your job locally, find out how long each model evaluation takes, and then you can get an estimate of how much runtime you need to request on design safe. So in this case, I'm just going to request 20 minutes. I'm not going to change this. This job will not finish within 20 minutes. So when you actually submit a job, you have to set up the right time. And once you submit a job, you can click on Get from Design Safe. It shows the list of all the jobs that you have previously submitted to Design Safe. So this shows that the job that we just sent to Design Safe is being submitted to the job queue and will be picked up shortly. And then once you run the analysis, you can also retrieve the results. So if you click on the job, it will show you options to retrieve data. So once your job has finished running successfully, so it will show, you can click on retrieve data, and then you will be able to get the results back into quoFEM. So right now the job has not yet finished, so there is no data to retrieve. But I have run the analysis previously, and I have saved some of the results in this file. So these are again JSON files. So after retrieving the data from Design Safe, I had saved the file as a JSON file, and those are the JSON files that are here. So I can again just open the results. So these are corresponding to these. This file shows 1,000 samples drawn from the posterior. And if I click on the results panel, this is the kind of results that you'll expect to see. So it will show you what is the mean and the standard deviation of the parameters that you calibrated. But since this is Bayesian estimation, it also gives you the entire samples which show you the entire joint distribution of the parameters. So if I click on the data values tab, you can see how you can visualize pair plots of the different samples of your input values by left clicking and right clicking on the columns. Okay, so this is how the results will look like once you do the Bayesian calibration. And after that, you can save the sample values that you obtained by doing the Bayesian calibration. So let me go back to that folder. I'll just try to save the RVs in this directory. So it's taking some time to save. So you can save also the different columns separately, as well as you can save all the quantities of interest. So the quantities of interest have the outputs. And you can save the entire table also into a CSV file. So while that is going on, I'll quickly show you how to show you some of the other analysis as well. So in addition to the Bayesian calibration, there is also the global sensitivity analysis. So if you click on that file, it will load. It will populate the different inputs that are needed to run the global sensitivity analysis. We used, again, the same model, the analysis script article, to do the sensitivity analysis as well. And again, I have the results from a previous run. So let me load those results of the sensitivity analysis. So you'll see that at the end of the analysis, you'll find this panel, which shows a summary of the different sensitivity analysis. There are two types of sensitivity indices that are computed. One is known as the main effect sensitivity index, and the other is the total effect sensitivity index. So both of these are shown and are available to you as well. So what do these mean? So let's say if I plot, I'm looking at the sensitivity of n cycles 1 to the different input parameters, to the 3 different input parameters. So if I observe how n cycles 1 is affected by dr, we see that at low values of dr, the n cycles 1 has a small value. But as the value of dr increases, there is a clearly evident trend, a clear dependence on the value of dr. So n cycles 1 has a clear dependence on the value of dr. But if we observe n cycles 1 plotted versus d0, we don't observe as much of a clear trend. Maybe at higher g0 values, there might be. And also if I plot it versus HP0, maybe at higher HP0 values, we might see that n cycles 1 has a higher, has some dependence. So this is what is quantified by the main effect sensitivity indices. So it shows you that the n cycles 1 is highly dependent on dr and not so much on g0 and not so much on HP0. So you can use this kind of information from your model to decide which of the parameters are influential and which of the parameter, which of the uncertainties and the parameters you can ignore. So you can maybe just set G0 to a particular value. Since it is not affecting the uncertainty in the output much, you will be able to reduce the dimensionality of the input parameters that you need to calibrate. So you can do a global sensitivity analysis as the first step, as a preliminary step before doing Bayesian calibration, if you are interested in reducing the number of parameters that you want to calibrate. And after doing Bayesian calibration, we can then save all the data into text. quoFEM will let you do this. So you can save the different columns into data files. And once you have these sample values, you can then do forward propagation. So if I load the input file corresponding to the forward propagation, it will show you that dr, g0, and HP0 are sample values coming from a correlated data set. So in the pair plots of the samples from the posterior, you observe that there is a clear dependence or correlation, not just correlation, there's also like nonlinear dependence between dr, g0, and HP0, the parameters values that we calibrated. So all of that information about their joint distribution is captured in the samples. So you need to make use that you use the corresponding values of dr, g0, and HP0. That is done by letting quoFEM know that you want to resample the random variables from a correlated data set. And we have set up a forward propagation here using SimCenter UQ. So SimCenter UQ supports this option of using samples that you obtained by doing Bayesian calibration in quoFEM for doing forward propagation. And in this case, I'm using a different tickle script, which is in the same directory here. This tickle script sets up an analysis of the soil column for that I had shown on the slides before. Again, these are the three input parameters in this case. So we are getting the values from the data. We are providing the data set of the values, sample values of these parameters from these text files. And these are the values that were obtained by Bayesian calibration. And in this case, we have several quantities of interest, since we're interested in the profile of the lateral displacement along the length of the column. Again, we can run this analysis on design safe. So with that, I'll just get back to my slides and I'll show you the kind of results that I'll just summarize the results that we just obtained. So by doing global sensitivity analysis, we discovered that this variable dr dominates the response. So here I'm showing the number of cycles on the y-axis and dr. This is a log scale, so that's why you see a linear trend here. Whereas in within quoFEM, you observed an kind of like an exponential dependence of the number of cycles on dr. So this is the kind of results that you get from sensitivity analysis. Now from Bayesian calibration, I'm showing pair plots of the sample values of dr, g0, and hp0 in this plot. So these sample values characterize the posterior probability distribution of these parameters after doing the Bayesian calibration. Now corresponding to these sample parameters, parameter values, we also have the predictions of the output quantities of interest at each of those CSR values. So this is also available to you in quoFEM. So quoFEM gives you the input parameter values as well as the corresponding outputs. I've just used that table to plot the output to obtain the range and the mean value of the predicted output quantities of interest at these different CSR values. So we see that these red dots were the data that were used in calibration. And after calibration, the mean of all of these predictions is doing a reasonable job in matching the data that we used to do the calibration. So that's what we observed from that. And finally, if you run the forward propagation analysis, you will get so there were so many quantities of interest in the end. So if you plot the residual displacement corresponding to the different elements that are part of your soil column model, then this is the kind of displacement that we see. So in this soil column, there are 3 layers, and the middle layer is the layer that is susceptible to undergo liquefaction. So that is what we have seen here. So under the action of a seismic excitation at the base of the soil column, the seismic excitation was enough to cause liquefaction within that middle soil column layer, and that underwent significant residual displacement at the end of that seismic excitation caused by liquefaction. And this shows the uncertainty in the profile of that lateral displacement that is caused purely due to uncertainty in the input parameter values that we passed in. So that was just a summary of the example as well as today's session. I'm coming to the end of the presentation. So we have some upcoming features of the quoFEM that we're planning to release. Will be enabling multiple model class selection and averaging. And we want to also support multi-fidelity Monte Carlo. So where we use surrogate models in addition to the high fidelity, computationally expensive computational models to enable not just efficiency in the UQ, but also accuracy. So that's the intention behind implementing multi-fidelity Monte Carlo. And we also want to use the surrogate models to help in Bayesian model updating. So this is something, again, which you can expect to see in some of the upcoming releases of quoFEM. And I again wanted to highlight that we have UQ office hours. So there is an announcement in the SimCenter forum. Sangre also shared the link with you. So please feel free to check in to our UK office hours, and we're very happy to talk to you and offer any help that you might need in running analysis with quoFEM. You can also reach us through our SimCenter forum, and there are some upcoming live expert tips that have been scheduled. And yeah, these are very exciting topics, and I'm really looking forward to those as well. So that brings me to the end of my talk. Thank you very much. I'm almost at the end of time. Sorry for taking so long.
Well, it was very comprehensive. So thank you, Aakash, very much for the presentation and going over those examples. It was certainly informative on an entire process of starting from experimental data and working all the way through to calibration and then forward. Yeah, it was a great example. So thank you for going over all of those. We have a couple of quick questions. We're over time, but I think that if we can answer them quickly, we ought to. So one quick one is, does quoFEM support OpenC's Pi models?
Yes, we do. Yes, we do. So if you go to the Python, if you choose the Python FEM engine, that will let you pass in any Python script, so you can have an OpenC Pi model.
Great. Does quoFEM support random field models?
Yeah, so we don't have generations of like stochastic fields, random fields yet. That's something that we want to add in the future. Sangri, do you have anything else to add?
She won't be able to unmute. Let me.
Okay.
Now she can.
Random.
If not, maybe another option is going to the SimCenter forum, which we showed you the link to earlier, and adding that as a feature request to quoFEM will be one way of getting that added as a to-do list to our areas for improving the tool. One other question, do you have any good references or resources that would provide appropriate distributions to use for specific engineering components or materials?
That would depend on the problem. I would say, like, if we know nothing more but the mean and the coefficient of variation, then you can use a normal distribution. But if you know that the random variables have some lower bound, so they cannot take positive values, or they cannot have values lesser than a value. So if there's some lower bound, you can use a log normal distribution. If you know that there are both lower and upper bounds, you can use a beta distribution or a uniform distribution. So beta gives you more flexibility. Those are just kind of like the general guidelines, but it's very problem specific, and it depends on the problem.
Mm-hmm. Okay. One last, maybe two more questions. The example you showed had only a few random variables. You were able to narrow those down in order to be maybe more efficient in the forward propagation steps.
Right.
Will this method still work, or does it really slow things down if you have many more unknown or random variables? Maybe 20 random variables and hundreds of measurement data points to try to calibrate. Where do things start to break down in terms of this expanding as an example?
Right. So yeah, the example that I showed, there were only 3 parameters that we were calibrating, but we have done some work before where there were around 36 parameters. So it's able to handle like reasonably larger number of input parameters, the Bayesian calibration algorithm. So there isn't anything inherently limiting the dimensionality of the parameters that can be calibrated. Yeah, it gets more challenging if we have more data, because this is trying to fit the mean. And the more data we have, the more confident we become in our estimates of the posterior. So a lot of the uncertainty will not be captured in the posterior parameter distribution for the model parameters, but it will be captured as noise. So that becomes an issue. And when it comes to, when there are more input random variables. So the methods that are available through Dakota for doing sensitivity analysis can do reasonably well. And we also have previous live expert tips that showed us how to handle high dimensionality in the outputs when doing global sensitivity analysis. So that's again something that can be checked out.
Okay, and the last question, you mentioned that quoFEM and actually all of the SimCenter tools are open source. How would somebody access the GitHub repo for the SimCenter tool?
Yeah, I had not shown. So if you can go to our GitHub page as well. So if you search for NHERI SimCenter GitHub, that will take you to our GitHub page, and here you will find all our source code. So if you, for example, click on quoFEM, that will take you to the quoFEM repository. So this is how you can find all our software all the software that were developed are open source. They are located on our NHERI SimCenter GitHub page.
And I might add that a direct link to the source code for each particular tool you can find on the tools webpage, which is at our webpage. So going to our landing page, simcenter.designsafe-ci.org, and then navigating to the particular research tool, in this case quoFEM. On the right side, you'll also have a link to the, actually it's on the bottom, it's not on the right side. Here. Down at the bottom is a link to the GitHub page. Yeah. So thank you for those questions from the attendees. Aakash, thank you again for the presentation, for the examples and demonstrations. We really appreciate it. This concludes today's live expert tips brought to you by the NHERI SimCenter. We hope it's inspired you to pick up the quoFEM tool and the examples that Aakash presented and adapt those capabilities to your research. Thank you very much for everyone for being here.
Thank you all.